Finding the negation of a universal statement can be a little counterintuitive. There's a temptation to just replace all with none and move on, but it's not quite that simple. Remember that a statement and its negation have to cover all possible situations. For example, the negation of it's raining is it isn't raining, and there are no other possibilities. Either water is falling from the sky or it isn't. Right? This isn't the case with all dogs versus no dogs. Suppose, for example, that exactly 3 dogs can swim. Right? That possibility isn't covered by either the all case or the no case. So no dogs can swim is too strong a statement, and we're going to need something just a little looser. Right? So to come up with the correct result, remember what we need to do to prove a universal statement is false. All we need to do is come up with a single counterexample, right? In this case, a single dog that can't swim, and the original statement must be false. So the negation of our universal statement will actually be an existential statement. That is a statement about the existence of that one animal. There exists a dog that can't swim. Now, grammatically, yeah, that's a little awkward, right? And there are other ways we could phrase this. For example, some dogs can't swim, or at least one dog can't swim. Right? Those would all be equivalent English versions of the negation that we're looking for. Now, procedurally, the way I remember how to do this is you replace all with some, and then you negate or reverse the descriptive part of the original universal statement. Right, so what I have here, this just formalizes what we talked about on the previous slide, right? The negation of a universal statement is logically equivalent to an existential statement where the predicate part is negated. All right, so I think the negation of an existential statement is a little more straightforward. The only way there exists a dog that can swim could be false is if there isn't a single dog that can't swim. There isn't a single dog that can swim. In other words, what I have here, no dogs can swim. And that's a perfectly good English phrase, right? But we like to phrase this using the language of a universal statement. And we can do that with this version here, all dogs can't swim. Right? Now, notice how the pattern we saw for negating a universal statement repeats here. The existential qualifier, there exists, becomes a universal qualifier, and again, the descriptive part gets reversed or negated. And again, I've got the same formal phrasing here that we did with the negation of universal statement, right? There exists becomes for all, and Q of X, right, the predicate part becomes not Q of X. So it really is the exact same sort of procedure we saw previously. All right, so I've got some examples here for us to look at, and the key thing to remember here is to apply our process. Existential statements become universal statements and vice versa, and the final predicate gets negated, right? And if a statement doesn't obviously fit one of those two molds because of the English syntax used, rewrite it that way. That is, rewrite it as a clear, universal, or conditional statement first, then write the negation. Don't try to get creative with the negation part. Just apply the process first. Then, if you think it's necessary, you can clean up the English syntax second. All right, so let's see what we've got going on with the examples here. Right, the first one, all words. This is an existential. This is a universal statement, and have vowels is the predicate. So if I wanted to write the negation of this, that would be, remember, all becomes there exists. There exists a word that doesn't have a vowel. Right? And that's not bad from an English perspective. You know, you could leave it that way if you wanted, or you could, for example, rephrase it. Some words don't have vowels, right? That would be an equivalent English syntax. All right, so let's see this one. Some cows. It's clearly not a universal statement, right? It's not talking about all cows. It's talking about some. So this is an existential statement. So we've got some cows produce milk. Okay, so some is the existential part. So for the negation, this is going to become all. Instead of some cows, all cows. And produce milk will become don't produce milk. All right, so the third one here, every integer is a real number. Okay, we're talking about every integer, right? So this is a universal statement, and it's talking about numbers specifically, integers versus real numbers. So I think we can probably go directly from here to the negation, but if you need to, right, this is equivalent to, for every integer x, x is a real number. Okay, now we can go. As a matter of fact, let's do the logical version here. There exists an integer x such that x is not a real number. Right, now we're doing it kind of with the logical forms, right? And that's fine. If you wanted to rewrite this in English, you could do something like, there is an integer that is not a real number. Okay, so how about the last one, right? This one is a little interesting, right? Not all functions are continuous. Okay, so this one is, yeah, a little interesting. It's got that all in it. So you could be forgiven if you looked at this and started to think that this was somehow a universal statement. But it isn't, and it's that not that makes that happen, all right? Not all functions is the same as some functions are not. So I would think of this as some functions are not continuous, and now it's starting to fit a little better into our existential versus universal molds, right? Because we're only talking about some functions. This is in fact an existential statement, right? So this is saying there exists a function f such that f is not continuous. And now we can go to the negation, right? The negation would be, let's see, the exist becomes all functions, and we're gonna reverse the predicate part. All functions are continuous. And there's our negation. Okay, so how about a universal conditional statement? Well, the negation of universal conditional statements are particularly important in mathematics, and fortunately, we can derive this from principles we've already worked out. Okay, so first, we need to do the negation of the universal part, and we saw it earlier in this lecture. That is going to be there exists an x such that not p of x implies q of x, right? And we've already seen that the negation of an implication of the arrow here is an and statement. So that makes our negation there exists an x such that p of x and not q of x, right? Or another, the negation of the universal conditional is equivalent to this existential statement, and that's what I've written out here, right? We've got the negation and the universal conditional over here. We've got, I know you just a minute ago, we haven't seen this for a little bit now. This is the logical symbol for equivalent, right? It's the logical version of equals. And over here, we've got the existential statement that we just derived. All right, so how can we use this, right? I've got three universal conditional statements here, and I want to write their negation, right? So remember how we're going to do this. The for every becomes there exists, and then we're going to take that if then and convert it to an and. So the first one would be there exists a rectangle such that all four sides are congruent and it's not a square. And that's my first one. Right, now you go ahead and pause if you like. Right, go ahead and try doing these second two. Right, then start up again and see what I come up with here. All right, so again, we've got for every real number, this conditional has to be true. And right now for this one, let's go ahead, just kind of for practice, because it's easier to do when we have algebra expressions in here. I'm going to write the universal, the logical form. So this is for every x, an element of the real numbers, x greater than 0 implies absolute value of x equals x, right? And we want the negation of this. So we kind of saw the logical equivalence in the logical form on the last slide. So we know what's going to happen here. It's going to be there exists an x that is a real number such that x is greater than 0 and the absolute value of x is not equal to x. So that would be our negation. All right, again, for this next one, we'll go ahead and do this in English, right? The negation of this function statement would be there is a real valued function. We could have said there exists there, such that it is. See, I slipped here, right? It really, now I was at a loss because I didn't have the variable to work with. Let's go and slip the variable in here. There is a real function, there is a real valued function f such that f is differentiable but not continuous. There you go. Right. Sometimes when you're doing the English version, you don't want to mention a variable because it's not a very English syntax kind of thing to do, right? But it's a good idea to slip it in there, especially if you're looking ahead, right? See if you're going to need it for the second part of the statement. Okay, so that's how we can do the negations of all of these three different kinds of statements we've been talking about here. In the next lecture, we're going to see how we can use this to answer a really kind of odd question. If we have a situation where, if we have a situation with a universal conditional statement where it's impossible for the P of X part to be true, then what happens? Right, that's got a name. It's called a vacuous statement. Right, and that's what we're going to talk about in the next lecture.